Good afternoon. This is CIVE 634, Surface Water Hydrology. And today's class is 141, and that is 141, the 14th week, the first class of the week. Since Wednesday, it's a Thanksgiving holiday, we're not going to have a 142. The subject today is the last session or the last class on stream channel routing. We left on H10. So today we're going to do H11, H12, H13, H14, H15, 16, 17, and 18. We got to do all of them today. So let's get going here. It's a lot of coverage. The first thing I'm going to do, some of these subjects I'm going to have to run. Others I will wait, and just there's some videos in there and so forth as usual. But the concept or the subject today is Introduction to Dynamic Waves. We have already, and this is a chapter in my book, in my hydrology book, chapter 9. We have already covered kinematic waves. We have already covered diffusion waves. And now today we're going to cover dynamic waves. Now, what's the difference? We already know the difference, but let me reiterate that. Kinematic waves do not attenuate. Are there kinematic waves out there in nature? And the answer is yes. A lot of flood waves are kinematic. They don't attenuate. That's why they are flood waves. The next type of wave is a diffusion wave. The diffusion wave diffuses a little bit. The British have said in the year 1975, with their experience, that if within one period of propagation, the wave diffuses less than 30%, it is a diffusion wave. Okay, fine. And then after that, then by exclusion, if a wave diffused within one period of propagation more than 30%, it would be a dynamic wave. But then the question is, how many dynamic waves are out there? And the answer is, in my practice and in my opinion, very few. And I have a backup to say that, very strong backup. But at any rate, we'll get in there. So the dynamic waves is a fancy way of talking about hydrology, but they technically don't exist, or there's only a very few instances where you could say that you have a dynamic wave. Specifically, an instance where a dynamic wave may be the case, it's a dam break. When a dam breaches, the reservoir releases a wave of water. The wave usually lasts about an hour or two to release, like in the case of Teton Dam. And in that, an hour or two to release is not enough time for the wave to be kinematic. So therefore, or even diffusion. So therefore, it is a dynamic wave. So dynamic waves do exist, but they are largely to be found, okay? In other words, you have to look very hard to find them. This statement was said not by me, but no other than Lighthead and Whittam in 1954. They clearly said in their paper, if you read all their paper and every instance of their paper, every element, that they said that the dynamic waves diffuse very fast and the mass goes on to form the larger, slower moving kinematic wave. That is a truism. We know that for a fact. Okay, so this is the intro to a dynamic wave solution. How do we solve a dynamic wave solution? Well, let me back up a little bit. The kinematic wave, the solution of the kinematic wave, 1973, 1980, etc. Several people that worked on this. Will Heiser was one of them, actually earlier than 1973, 1967. Will Heiser, Shaki also, 1965, MIT 73. Anyway, a bunch of people solved the kinematic wave, but they solved it in an incomplete fashion, as I show in my book, in this chapter, as a matter of fact. Then came the work of Conch and the following by myself and several other people, where we argued quite convincingly that the diffusion wave was there to stay and that it should be used more broadly, more than the kinematic wave. And then finally, the dynamic wave. The dynamic wave as a concept was developed, well, it was there, but it was not until Danny Fred did his work in the year 1973 at Missouri Rolla that he came up and said, this is the solution. I'm going to use the Priceman scheme, and we're going to solve the dynamic wave, the complete Saint-Venant equations. He argued that once you solve the dynamic wave, that you didn't have any business solving the kinematic or diffusion waves because they were lower order. meaning less accurate. And of course, in my mind, he was wrong, but he was he. I mean, he worked for the National Weather Service for 40 years, and that was it. Now, after Danny Fred, now he passed away maybe 5-6 years ago. The question is, what are we going to do after Danny Fred? Because Danny Fred argued that the dynamic wave was the only way to go. Other people, myself and others, have argued that no. As a matter of fact, the dynamic wave has a tendency not to exist in practice, other than the dam breaches. And not every wave is a dam breach. So that's the story as we know it. Okay. So the stream channel, in order to solve a dynamic wave, and this is briefly, I did not solve the dynamic wave in my book because I thought that that was hydraulics, not hydrology. The stream channel is divided into several computational reaches for computational purposes. And we apply the Priceman scheme, which we learned in computational hydraulics. I don't cover here the Priceman scheme. It's a numerical scheme developed by Mr. Priceman in 1961 in order to do this, in order to solve the dynamic wave. Let's say that at the beginning of the 60s, when the computer was becoming widely available, all the top researchers across the world in hydraulics felt that they had to go to the dynamic wave. We must go to the dynamic wave. Priceman did it, Kunz did it also. And then subsequently, people like Danny Fred came afterwards. Fred, by the way, is spelled F-R-E-A-D. Danny went on to work with the National Weather Service. He developed several models in the National Weather Service of the dynamic wave, et cetera, et cetera. Okay, so the application of the Priceman scheme to the governing equation results in a matrix, and then you got to solve the matrix with a so-called double sweep algorithm. The matrix turns out to be a sparse matrix, meaning a matrix is like a square, but this particular matrix only has elements in along the diagonal. So it's kind of a diagonal solution of a matrix. That's called double sweep in the jargon of numerical mathematics. Double sweep. Double sweep is because you start on one end, pick up a boundary condition, you sweep to the other end, pick up another boundary condition, and then you return to the back to the original end and sweep for the second time, and then get the answer to the problem. Okay, I remember that when I went to Colorado State in September 1973, that's the first thing that Professor Mahmoud confronted me with. He says, Ponce, we got to do the Priceman scheme. Here it is. And the double sweep, here it is. He showed me where it was. And then we got the Exner equations. In other words, the kind of same banana equations, but with sediment, on top sediment, which is called the Exner equation. We learned that in sedimentation engineering, not in this class. Okay, so that is solved, and that can be done. But there's ifs and buts in regards to this. First of all, there's the issue of whether the wave does exist at all, but that we'll settle that issue later on. The second issue is that you need a boundary condition upstream and another downstream. Otherwise, you can't solve it. Otherwise, you're going to have one less equation. In other words, we have in here, for instance, 5 reaches, right? 5 reaches, and there's 2 equations, so there's 10 possibilities. And we have one, I'm sorry, that's the reaches, but the cross sections are 1, 2, 3, 4, 5, 6. There's 12 cross sections. So if we put in one boundary condition, we're going to be short. We have to put 2 boundary conditions in order to be okay. So you're going to have 10 equations, right? 10 equations plus 2 boundary conditions that would solve for 12. Unfortunately, we don't know the downstream boundary condition. We don't know it. That's what we're trying to solve for the downstream boundary condition. So then it becomes an indeterminate problem, which it can be solved, and it is solved. But let's just look into that later on. But the issue in here, in my book, was the issue of the relevance. How come the dynamic waves had not been really considered to be hydrology? Because they are not relevant to hydrology. And since we're talking about a hydrology book, then I decided to put in here relevance of dynamic waves to engineering hydrology. Why do I say that? The dynamic wave is part of HECRAS, but it's not part of HMS. And HECRAS is the hydraulic model of the Army Corps of Engineers. HMS is the hydrology model. So there must be something in there that made the Corps not to put the dynamic wave into HMS. They would never do it because they consider that's hydraulics, not hydrology. So dynamic waves are often referred to as hydraulic river routing. As such, they have the capability to calculate unsteady discharges and stages when presented with the appropriate geometric channel data and initial boundary conditions. The relevance to engineering hydrology is examined here by comparing them to kinematic and diffusion wave solutions. And then I talk about kinematic waves. Kinematic waves have only one rating. That's easy, because the fact that you have a loop in the rating means that you already had diffusion. And since the kinematic waves don't have diffusion, don't have a loop in the rating, it follows that they don't have diffusion. Okay. Now, the diffusion waves have a little bit of a diffusion, and therefore they have a loop. But the loop is so small that we can neglect it, typically, in most cases. We can do a solution not to neglect the loop, but that's another story, more complicated. Now, and finally, the dynamic waves rely on the physics of the phenomena as built into the governing equations. A loop rating is produced at every cross-section. For any given stage, the discharge is higher in the rising limb and lower in the receding limb over here. The rising limb is over here, the receding limb. The discharge for any given stage, the discharge is higher in the rising limb than in the receding limb. That has to do because of the fact that the wave does have the slope. The water surface slope going up is not the same as the water surface slope is coming down, because there's a wave in there, right? So that's the issue here. There is a loop and there is a hysteresis of the wave. Now, the width of the loop is a measure of the flow unsteadiness. Wider loops corresponding to highly unsteady flow, that is dynamic wave flow. So basically, the dynamic wave is going to have a wide loop, and the loop is going to be so wide that it's going to drop itself, and all its mass is going to go on to form part of the underlying kinematic wave, which coming back is coming in there at a much slower speed. That's what Lighthead and Whittam said in 1955. If the loop is non-existent, the flow can be approximated as kinematic flow, and that is correct. The preceding observations lead to the conclusion that the relevance of dynamic waves in engineering hydrology is directly related to the flow unsteadiness and the associated loop in the rating. For highly unsteady flows, such as dam break flood waves, it may well be the only way to properly account for the loop rating. For other less unsteady flows, just typical flood waves, kinematic and diffusion waves are a viable alternative, provided their applicability can be clearly demonstrated. So the history of the channel routing in hydrology and hydraulics, because at this point, we cannot set them apart, because it turns out that routing sits in the middle between hydrology and hydraulics, right? So some people consider it hydraulics, hydrology. There is confusion, and not in my mind, but there is confusion in fact into the issue of whether channel routing is indeed hydrology or hydraulics. But this is just a name calling or notation. We know what actually happens, okay? Now, in addition to what I just said, which is the solution by solving this dynamic wave, or rather the Saint-Venant equations, in two separate equations, there is also the combination of them into one equation, a procedure which was started by Hayami in the year 1951. What did Hayami do? A gentleman from Japan. He took the two equations, continuity and momentum, combined them into a diffusion equation. And he started calling this diffusion equation. This is the diffusion equation, the complete, or rather the more complete diffusion equation of Hayami. The only difference being that Hayami did not come up with this, the parentheses. He didn't have this. He just had this. And he called this, or everybody calls this, the Hayami diffusivity, this over here. Can you see that? Can you see what I'm circling? You do, right? Hello? Hello, where's everybody? Cassidy?
We can see your mouse.
Okay, thank you. I just want to confirm. What the mouse in here, what you see in here, the mouse, that's the Hayami diffusivity. Hayami did not present this equation over here, or this extension over here. This was presented by Doug later on, as well as other work that we did, but this is the complete equation. And then eventually, I was instrumental in finding out that this beta beta minus 1 squared, fruit number squared, is indeed the so-called Vedernikov number, which we now pair with the fruit number. You heard me talk about this before. So equation 981 turns out to be the complete combined convection diffusion equation. Convection is over here. There's the amount. Convection, and diffusion is over here. That's just a convection first order term with a sediment celerity in the front. And this is the diffusion second order term with the Hayami diffusivity, complete Hayami diffusivity with Vedernikov number dependency. So that's the story. As to, can this be solved? Yes, this can be solved with the Muskingum-Ganch method, the gradient dependence. We've done this since 1986, as well as in other applications for hydrology now. Now for hydrology. You see how there's confusion. There's confusion. So at any rate, so that's the story of the dynamic wave as written in my book. Now, we're going to now move in here, and which is kind of an old video, but it's a nice video. Causes of runoff diffusion. Very important for what we're studying here. What is the cause of runoff diffusion?
Runoff diffusion is the spreading of stream flows longitudinally and or transversely, which leads to a reduction in peak flows. Runoff diffusion is responsible for the size and magnitude of flood discharges. What causes runoff diffusion? There are natural and artificial causes for runoff diffusion. In large watersheds or river basins, the flow spends most of the time in the river channels. In river channels, diffusion can be longitudinal and or transversal. Longitudinal diffusion is subject to Hayami's law. Hayami's law states that the coefficient of hydraulic diffusivity is directly proportional to the unit width discharge and inversely proportional to the prevailing channel slope. Therefore, the larger unit width discharge and or the smaller the prevailing channel slope, the stronger the diffusion effect. The transversal diffusion coefficient is usually about twice the longitudinal diffusion coefficient. Thus, very large unit width discharges and or very small slopes are extremely diffusive. Diffusion causes spreading of the flows, increasing the chances for infiltration and reducing runoff peaks and volumes. Flood discharges depend on the prevailing slope, which in turn depends primarily on the watershed or basin size, and secondarily on the stream or river cross-sectional characteristics. The purpose of flood routing is to calculate the amount of runoff diffusion. Flood routing is the calculation in time and space of a flood hydrograph based on the geometric and hydraulic stream channel characteristics. For small unit width discharges and or large prevailing slopes, runoff diffusion may be effectively reduced to a negligible amount. A flood wave that is not subject to diffusion is referred to as a kinematic wave. In the absence of runoff diffusion, routing is based only on convection, that is, on the travel speed of flood discharges along the channel. The travel speed obeys Sedlin law, which states that the wave velocity or celerity of a certain discharge is equal to the slope of the discharge stage rating at that discharge divided by the channel stop width. In general, a stream channel routing method must account for the Sedlin and Hayami laws. Only then would the stream channel routing method be physically based. Unlike natural runoff diffusion, artificial runoff diffusion is produced by man-made reservoirs, which exert a diffusion effect, spreading the flows in time and space. Routing through reservoirs depends on the geometric characteristics of the reservoir and on the geometric and hydraulic properties of the outflow systems, be it closed.
I was amazed when I first saw this spillway back 20 years ago, a little more than that. I believe it was 80. This is the spillway that failed at Oroville. This was the emergency spillway, the largest spillway of its type built in California, and I'm not sure of the world. Well, like I said, when I saw many years ago, I've been there 2 or 3 times over the course of 30, 40 years. I was really amazed of its size. Well, it's a lion, but It's more like a mouse, because that day on February 10, 2017, it failed miserably, tremendously. It failed. You've seen it. You've heard about it. Oroville spillway failed. The first spillway failed, then the second spillway failed. Had it continued to rain, it would have created one of the major disasters ever to be produced by hydraulic engineering. Fortunately for us and for everybody involved there, when the reservoir got full, the two spillways failed, and then it stopped raining. How about that? Can you believe that? Thank God.
This conduit for free overflow spills.
Okay, so the S-curve explained. In here we have a video, but I'm just going to go with the vector here today. Mostly because I know you guys realize by now, the S-curve is my topic. And the explained, I mean, I know this back and forth, left and right. But let's go ahead. You all have the backup of the video. I'm not going to show the video on this one. Remember, I choose between raster and vector. Here, vector. So let's look into this, how do we explain the S-curve. We wrote this in the year 2019, basically because people were coming back to me and saying, I don't understand this, I don't understand this, because it was difficult, mathematically speaking. So the dichotomy between kinematic and dynamic waves and its relation to scale has defied complete understanding in the past. The matter has been elucidated by Ponce and Simons, who identified the appropriate dimensionless wave number and plotted dimensionless relative wave celerities across the spectrum of dimensionless wave numbers. Okay, in addition, they clarify the propagation characteristics of various types of shallow water waves, including the celerity and attenuation. So here we review. They explain the theory. For those of you that took up computational hydraulics, that's right, computational hydraulics and hydrology. Last year, this is kind of repetition, but many of you have not. Forces and wave types, we got 4 forces in open channels, unsteady flow. We have the friction over here, gravity, the pressure gradient. Those are the ones that can be plotted on the graph. There's one fourth one that is called inertia, which cannot be plotted. The inertia is the unbalanced force, meaning, according to Newton, if there was a force that was unbalanced, there was a force that came up against of the same magnitude in a different direction. That's called inertia force. We could not plot inertia force in here. But there's 4 forces, right? Gravity, gravitational force, friction at the bottom, pressure gradient, which is the difference in depth between upstream and downstream, and inertia. So then the question is, now going back to notation and what we call things, is what are the wave types? Kinematic, we know now, it's gravity and friction. Diffusion is gravity, friction, and pressure gradient. Here we get into a misnomer, a semantic problem. After 1973, when Danny Fred started calling the mixed kinematic dynamic wave, he started calling it dynamic wave. It was a mistake, but it got very prevalent around the world, around the United States. So in my mind and in my books, dynamic wave is just the pressure gradient and inertia, a concept defined by Lagrange in the late 1800s. So 240 years ago, Lagrange was saying that the pressure gradient and inertia combined create the dynamic wave. But then there was like I say, 1973, almost 200 years later, somebody came and said that the whole thing in here, it's dynamic, as we say in here, dynamic wave. So it's a confusion between what Lagrange called it 220 years ago or 240 years ago, and Fred called it in the year 1973. So in here, to kind of hit the middle road, we call it mixed kinematic dynamic wave. So in reality, this should be the Danny Fred wave. But we call it, we don't want to give it the name Danny Fred. He's dead already anyway. So in this book, in my book, it appears like that: mixed kinematic dynamic wave, and then the dynamic wave of Fred. Okay. Our kinematic waves. This is just so confusing for many people, both hydraulics and hydrology. I have been around and I know We wrote papers over the last 40 years, and sometimes he came back saying, kinematic wave doesn't exist. It is an idealization, a creation for people like Professor Ponce, something like this. That is totally untrue. The dynamic wave, the kinematic waves do exist. And I show you here a kinematic wave. This is a kinematic wave featuring a flood wave period of 1 year. 1 year? Over where? In the upper Paraguay. And we've studied this river in the year 1979. And we discovered, not discovered, but documented in there the kinematic wave. This wave goes up starting in March, April, May, June, peaks in June, May, June, July. Then it starts coming down, and then it bottoms out at December, November, December, or January. Every year, there's only one wave in there, over at this Ladario place. Well, this one is at Puerto Murteño, which is downstream of Ladario. But at any rate, the kinematic wave does exist. So there's people out there that blindly follow the kinematic wave and think it's the best in the world, and among them, my Professor Wilheiser, and others that say, no, the kinematic wave is a bunch of poppycock, we should use a dynamic wave, among them, Danny Fred. Where's the truth? They're missing something. The truth is that the wave in the middle is the more realistic of all of them, the way that covers more area, that is more cases. That's the diffusion wave. Unfortunately, Wilheiser was unable to see it, and Danny Fred was unable to see it also. Kahn saw it, and then many others that followed him, among them myself. Okay. We quote from Leichhardt and Whittam, the kinematic wave property follows from the equation of continuity alone. That's true. We suggest that these waves be described as kinematic. They gave them the name at that time, 1955. The classical wave motions would, in contrast, be described as dynamic, depending as they do on Newton's second law of motion, inertia. So he's referring to classical wave motions of Lagrange. Everybody, I mean, that was known, well known, until Danny Fred came around. Okay, so classical dynamic waves transport only energy, the energy of Lagrange, the waves of Lagrange. Okay, it follows that mixed kinematic dynamic wave transport both mass and energy, because the kinematic waves transport only mass, according to Leichhardt and Whittam. So therefore, in the resolution of this dichotomy, what is it that the mixed kinematic dynamic waves transport is the strong attenuating tendency of mixed kinematic dynamic waves. They have a very strong attenuating tendency, and we'll get there. Our findings, how were we able to do this? In 1976, we discovered this number over here. We call it a characteristic reach length. Actually, Leichhardt and Whittam had already mentioned, they said that this is an important variable, but they didn't use it. We learned from them. Like I said, they did not complete their work. Leichhardt and Whittam completed their work, I would have nothing to do. But they didn't complete their work, and I followed through and I pursued this thing. I think I already mentioned that they got sidetracked in some other methodology, but they wouldn't get anywhere. But we didn't. We focused on this number, which is an absolute triumph in hydrology and hydraulics. Without this, we couldn't understand anything. But we did it. 1976, 1977. That's the number that you got to play around in, not play around, play into the, or introduce into the calculations in order to find out the truth. And the truth is this. This is the truth. What is this? This is a plot of the size, relative size, dimensionless wave number. The entire size range could be compressed into 6 orders of magnitude, from 0.001 to 1,000. So 1,000 or to 1,000 here, 6 orders of magnitude. And in here, we're gonna put the relative wave celerity based on the size. And we show that over here is the 7th speed. This is the 7th speed, is 1/2, but it's relative. So instead of being 3/2, it's 1/2. And over here, we got the Lagrange speed. So here we got 7th speed, and over here, the Lagrange speed. So which other speed is there? There is no other speed. There's a speed. In order for us to characterize a speed, it would have to be independent in a certain range of the abscissa. And over here, we have independence of the abscissa. So we have a speed over here that we can measure and characterize. Over here, we have also a speed, but over here, we don't have speeds because these speeds are varying with the size. Therefore, you can't track it. You cannot say this is a speed. And that is why prior to this discovery or finding, there were only two speeds, the Seddon speed over here and the Lagrange speed, which vary with the Froude number over here. But we found out that in fact, there was a link, a missing link, so to speak, between Seddon and Lagrange. Okay, and then we follow with the kinematic waves. We already seen that. And the kinematic waves what can I say, steepen or negative steepening. They can because they're nonlinear. But that's another more complexity into the issue. Let's leave that for the time being in here. The diffusion waves we already know, and the mixed kinematic dynamic waves. Okay, again, the mentioning of the Lichert and Whittam that said under the conditions appropriate for flood waves, the dynamic waves rapidly become negligible, and it is the kinematic waves following a lower speed which assume the dominant role. So again, we have in here our graph, but this graph is not the only one in our work. It is followed by this graph, which shows the attenuation, and it's very high attenuation in the middle. In other words, when the slope in here, when the second derivative gets to be equal to 0, that's when we have a peak over here. That's when we have a peak. And it shows a very strong attenuation over here, very strong attenuation. This is the log decrement, a measure of the attenuation after one period of propagation. It's a little fussy, how can I say, it's not 100% correct, or rather precise, but it is good. Okay, so we have in here the attenuation, So that explains the decay, extreme decay speed of the dynamic wave, or rather the mixed kinematic dynamic wave, the one in the middle. Because as you see in here, there's no decay, and in here, there's no decay either. Because note that this is logarithmic scale. So in one cycle of logarithm, we're going to 10 times. From here to here, 10 times, in effect, 10 times. So imagine there were millions times in here, because there's several orders of magnitude. But we also found out that if you go for a number greater than 2, then you're going to get amplification. So we were able with this theory to describe not only the waves, the flood waves that we would care to calculate, but also the pulsating roll waves that at this time people were not paying too much attention. That was in the 1970s, right? When Danny Fred did his work. But now we are, because we have a river in Bolivia that happens to develop these roll waves every month. And we're wondering what the heck's going on. And I've been working with them for the last 3 years, and we have published several papers on the subject, which of course we don't cover in this class. This is hydraulics. And here we're talking hydrology. You see, every time we want, we make a difference, and sometimes we don't. At any rate, so these are the graphs that complement the work that we did in the dynamic waves over here, the dynamic waves of Lagrange. The dynamic waves of Lagrange, again, the so-called S-curve, that's why I call it my S-curve. I'm the only one that calls it my S-curve, because it is mine and because it looks like an S, right? And finally, the roll waves. The roll waves are these waves that, pulsating waves that happen. And there's one thing in here that I have not researched, and I don't know, to be honest with you, because I'm a good engineer, but I'm not a dynamicist. I don't really get into dynamics. Dynamics is a very complex subject. We know that these waves, when are they going to be produced? What we do not know is why are they periodic? Why don't we just have one wave? Why we always have several waves in a train of waves? And this actually happens as a train of waves. I don't think anybody has seen out there one pulsating wave at Vedernikov 1.5 or something like this, because it is at Vedernikov greater than 1 that these waves happen. It's an absolute necessary condition for the formation of a roll wave that the Vedernikov number be greater than 1, which is Froude number greater than 2. So that's the summary over here. Kinematic propagation characteristics of various types in the shallow, in the stable regime, kinematic, diffusion, dynamic. And propagation characteristics of various types in the unstable regime, kinematic, mixed kinematic, and dynamic. So with that, then I have finished a brief explanation of the S-curve explained. So now we're going to move to the Atkin model. And in here, I believe, let me see this. No, we're going to show the video. And here we're going to show the video. You know, I jump around into raster and vector in here. To the left, my friend and client.
In the mid-1970s, I was pursuing.
To the left, my friend and classmate, Fred Thurer, Thurer. To the right, my esteemed professor, Everett Richardson, professor of hydraulic engineering at Colorado State University in the 70s and 80s. He passed away in the year 2012, I believe. But prior to that, he did a video, which I'm going to show you later on. The Atkin model.
In the mid-1970s, I was pursuing a PhD at Colorado State University and was fortunate to be at the right place at the right time. There, I had the pleasure of a close association with a select group of individuals from all over the world. One of these students was Frederick D. Thurer, Fred to his friends, who in 1975 completed a PhD under the supervision of Dr. Everett Richardson. After graduation, Fred rejoined his employment at the Natural Resources Conservation Service, the former Soil Conservation Service, or SCS, in Washington, D.C. Fresh out of school, he told his bosses that the convex routing method was no good and that it had to be replaced by a better channel routing tool. The convex method, developed by SCS in the mid-1950s, was a linear kinematic wave model featuring built-in, uncontrolled numerical diffusion. In practice, this meant that it lacked consistency. That is, a routed hydrograph could not be reproduced by substepping the reach length. In other words, the convex method was grid dependent. That is, two choices for space step would invariably give two different answers. Seeking a better routing tool, SCS developed in the late 1970s, with the help of Fred, the modified Atkin model. The method divided the routing into two sequential steps. The first designed to provide reservoir attenuation, the AT, and the second to provide kinematic translation, the KIN. While the model fared well in tests designed to prove consistency, it was not without its pitfalls. The matter was clarified in the 1990s when the theoretical accuracy of the Muskingum-Kunch method was demonstrated.
We have already reviewed this paper, by the way.
It is now generally accepted that the Muskingum-Kunch method is the only hydrologic channel routing method that is 1, stable, 2, convergent, and 3, consistent when used within its established parameter ranges. Unlike the convex method, the Muskingum-Kunch method simulates the diffusion wave model, therein its strength.
Okay, so we have, we're kind of a little bit ahead of us. Okay, let's do the raster in here, the vector in here first. The competition between kinematic and dynamic wave. Is there a competition? The answer is yes, totally and completely. I can tell you 10 stories on this because I lived through 40, 50, almost 50 years. But I'm not going to, I don't have the time. But you can search and look at my list of tales and you'll see a whole bunch of them dealing with the issue of kinematic vis-a-vis dynamic, okay? But there's one in here that is good. Kinematic waves are simplified models of unsteady flow. Is that a true statement? Yes, they are simplified. That doesn't mean that they're inaccurate. Simplification doesn't mean inaccuracy. It may well be reproducing the actual conditions in nature, right? Dynamic waves solve the complete equations of continuity and motion. That is the Saint-Venant equations. In 1849, Barré de Saint-Venant, a Frenchman, developed the Saint-Venant equations. And to this day, the Saint-Venant equations are respected and considered the most complete equations of unsteady open channel flow. That doesn't mean that completeness doesn't mean accuracy, by the way. I always state that. Based on this fact alone, it would seem that dynamic waves must be altogether better than kinematic waves. In a simplistic way, you can say, give me the complete equations and I'll forget about the others because they're not complete. Complete is what I want, right? That's what people say. Yet, and I say in there, yet experience indicates otherwise. In the classical paper on the theory of kinematic waves, Leahy and Whittam concluded the following. Under the conditions appropriate for flood waves, the dynamic waves rapidly become negligible, and it is the kinematic waves following at a slower speed, the 7th speed, which assume the dominant role. They already saw it. Woolheiser, the developer of the kinematic flow number, recalls how he and Liggett, Professor Liggett from Cornell in the 60s and 70s, started the joint research at Cornell University in 1964. Actually, joint research, Liggett was the professor and Woolheiser was the student, with the intent of showing that the Saint-Venant equations without simplification were required for the overland flow problem. I wasn't there, but I can almost see what happened. Woolheiser signed up with Liggett to do a PhD. Liggett said, you know what? I've been thinking about using the full, complete Saint-Venant equations to do overland flow because nobody's ever done it. Can you do it? And Woolheiser, being a student, what could he say? He said, yes, of course. Let's try it. And they tried it for a couple of years, I would say. This is what Woolheiser told me himself, by the way. They tried it for a couple of years and they couldn't get anywhere. Fearing that he wasn't going to graduate because he's not going to write a thesis on something that could not be done, Woolheiser convinced Liggett to not be so ambitious and say, let's go back under the kinematic. And Liggett, being a nice guy, agreed. He said, well, okay, Dave, I understand that. We cannot solve every problem in the world. So they reverted back to kinematic wave and they did the work on kinematic wave and created the kinematic flow number. Kinematic flow number, let me see what we have in here. Yeah, that's in my book. That's the kinematic flow number. This is a copy of my book, or a show of my book. 451 in my book is the kinematic flow number. Okay, so he created the kinematic flow number. Oh, I lost it here. I'm here. Yeah, the kinematic flow number, and they went on to become the most well-known pair of researchers that have studied the kinematic wave. I don't mean to insult anybody, but at the time there were several people. There were actually 3 people. Let's name them. I've already named them before. Woolheiser and Liggett out of Cornell, Shackey out of Princeton, and there was a guy, his name is Wooding out of Australia, somewhere in Australia. Okay. Actually, I'm not quite sure if it is Australia. I think that what happened was that Wooding was a New Zealander, but he went to Australia to finish up his work. And the reason why I'm saying that is because I had a list of great contributors of hydraulics and hydrology, which I still have on my site. And I had listed Wooding as Australian. And one day I got a call or an email from a gentleman from New Zealand. And he said, Professor Ponce, your thing is great and everything is good, but you made a mistake. I said, what? He says, well, Wooding is not Australian, he's New Zealander. Because I studied with him at high school. That was enough for me to understand that he meant business and he was correct. So I changed the listing of Wooding. Most people, though, don't know that. And they think because Wooding published in Australia that he's Australian, right? That would be the normal course of affairs. But at any rate, Wooding, Woolheiser, and Shackey, they, in the middle 60s, were working on the kinematic wave. Okay. Wooding recalled how he and Liggett started, Woolheiser recalled how he and Liggett started the research at Cornell with the intent of showing that the Saint-Venant equations were required. Yet, to their surprise, they came to quite different conclusions. That's what he told me. He eventually ended up doing only the kinematic wave. My question is, why didn't they do the diffusion wave? And the answer is, I honestly don't know. I would have to ask them. But I believe Dave, I'm not sure. I think he's still alive, Woolheiser. It would be interesting for him to go on the record and say that. And that, I say, go on the record. Will Heiser is a well-known guy on the watershed routing, and he was invited to give the Rouse lecture. And all the story was told none other than by Will Heiser in his own paper. And we already reviewed this, by the way. So theory tells us that kinematic waves do not attenuate, for sure, 100%. We reckon that many flood waves either do not attenuate or attenuate very little, for sure, 100%. Many flood waves do not attenuate, so therefore they're kinematic. Therefore, it follows that most flood waves must be kinematic, or at the very least diffusion, and not necessarily dynamic. So that's the story. That's the end of this. And now we're going to do, the video. We're pairing it in here. Vector and raster.
Kinematic waves are simplified models of unsteady free surface flow. Dynamic waves solve the complete equations of continuity and motion, that is, the Saint-Venant equations. Based on this fact alone, it would seem that dynamic waves.
On the many instances I have been in the field visiting for work, I have encountered flood situations several times, maybe 5 or 6 times over the course of 40 years. It's not a thing that happens all the time. Like this particular flood wave, we wrote it. My group, or the group of people that were with me at the time, we rode this wave. Imagine a flood wave and you start on top of it on a boat, of course. This is the Chané River in Bolivia, eastern Bolivia, on January 20th, 1989. We were on top of this wave.
Must be altogether better than kinematic waves, yet experience indicates otherwise. In their classical paper on the theory of kinematic waves, Lighthead and Whittam concluded the following. Again, under the conditions appropriate for flood waves, the dynamic waves rapidly become negligible, and it is the kinematic waves following at a slower speed which assume the dominant role. Unquote. Dave Woolheiser, the developer of the kinematic flow number, recalls how he and Liggett started their joint research at Cornell University in 1964 with the intent of showing that the Saint-Venant equations without simplification were required for the overland flow problem. Yet, to their surprise, they came to quite different conclusions. Theory tells us kinematic waves do not attenuate. We reckon that many flood waves either do not attenuate or attenuate very little. Therefore, it follows that most flood waves must be kinematic or, at the very least, diffusion, and not necessarily dynamic.
Okay. The issue of solving the dynamic wave is a very complex issue. As far as I know, Danny Fred, of course, worked on the dynamic wave. He became famous because of that, 1973. He was working with the National Weather Service, and he developed 2 models. The first one was called DWOPR, 1978. DWOPR means DW, Dynamic Wave Operational. It was an operational model of the National Weather Service, created and supported by Danny Fred himself, who became, with the time, chief hydrologist of the National Weather Service, okay? He also, subsequently, 3 years later, came up with another model that he called dam break. He spelled it D-A-M-B-R-K, dam break, which in my understanding was kind of a modification, slight modification of the DWOPR model. And why did he come up with 2 models? Well, I don't know, but I'm going to tell you my take on it. My take was, or is, continues to be, although he's long dead, by the way. Danny died 10 years ago. My take on this is that his dynamic wave model, his DWAPR, was not being used. And you know when models are not being used, I happen to know. But people were asking for about dam breaches, modeling dam breaches. So what he must have done, I think he exactly did that. He modified his DWAPR model, converted it into a dynamic to operate dam breaches, right? Specifically dam breaches. And he renamed it dam break. And he had a lot of success with the dam break because people going after looking for the dam break model, but hardly anybody was looking for the DWAPR model. So the DWAPR died because of lack of use. Over the 80s, middle 80s, you wouldn't see DWAPR. By the 90s, DWAPR was gone. Dam break was successful through the late 80s and early 90s and so forth. But then in the year 1998, I believe it was year 1998 or 2000, the Army Corps of Engineers came up with HECRAS with dam break. They did a dam break inside, not the dam break of the National Weather Service, some other dam break. And since the Army Corps has more wherewithal than the National Weather Service, they took over. So now if you want to do a dam break model, you go to HECRAS and you do it with the Army Corps model. You don't do it with DWAPR. I'm sorry, with dam break. And besides, Danny Fred died. I believe it was 2012. And with him, his model went down. So we don't use anymore. They're not used. Dam break or DWAPR, those two models of Danny Fred are not being used. Okay. Why I tell you that story? Because you should see the history of how things went all the way from the beginning. The beginning was in the 60s, and we have been doing this for 60 years now. Okay, so I have a picture in there about the instability of the Priceman scheme, which may be a little too much, but I like this figure because it's one of the first figures that we ever posted on the web, on my website. I believe it was 1999. As soon as I created my website, I had a student that was very good with Excel. So she created, I don't even remember her name right now, but I know it was a woman. She created this graph and we posted it on the web. What is this graph in here? This graph shows the instability of the implicit method of Priceman for the numerical solution of the Saint-Venant equations, weighing factor in the range 0.49 to 1. The graph shows only the beginning of the hydrograph. In other words, the hydrograph goes in here and it keeps going up. But we wanted to show in this graph the instability. So that's why if we show the entire hydrograph, we're going to miss the instability. So this is the answer. This is the situation. Now, what the heck is this? I mean, let's take a look at what we did in here. Graph. This graph shows the instability, meaning the lack of numerical accuracy, because the wave hydrograph should go a straight line over here. But this line is not a straight line. It is all ragged and such like that. Okay? Implicit method of Priceman for the numerical solution of Saint-Venant equations. So this is what Danny Fred did, the numerical solution of the Saint-Venant equations. But he and others used a weighting factor in order to avoid the instability. So in here, if you use theta 49, which is not recommended, you get the red, and the red is the most unstable. By the time you increase the theta to 50, 51, this is what the aspirant that I've been talking about in various places, I believe in this class too. By the time you get to 0.6, you get to the green. So it's this one over here. I believe so. 0.6 is the green one. And once it goes in here, and then it kind of is well behaved at the peak. I can't show it to you right now, but it is well behaved at the peak. So basically what people do in regards to running this model is artificially putting in there a whole lot of numerical diffusion, meaning aspirants, numerical aspirants, in order to control the model in these areas here, in these areas. So they use 0.6, 0.7, 0.8. They can also use 1, but 1's going to give them a whole lot of diffusion at the peak. They don't want to do that. So the ideal situation in here is to compensate. Don't use 0.5 because you won't be able to run it with 0.5 because they will have too many oscillations, too much oscillations. But if you run it with 1, it will cut the peak, and you don't want that either. So you settle for 0.6. 0.6 is the number that people settle. When you run HECRAS unsteady, HECRAS is going to tell you I'm going to use 0.6. If you want me to use something else, give it to me right now. Why do they use 0.6? Because they know 0.6 is the beginning of solving the problem. You can use 0.6, 0.65, but you should not abuse that, because then you lose the problem altogether. So this is kind of, I'm showing you this to kind of show you the complexities of the dynamic wave solution using the Priceman scheme. And that's the only one out of many, by the way. So it is a serious business. In such serious business that, like I say, I do not believe that there is a dynamic wave out there other than HEC-RAS. HEC-RAS dynamic wave. And everybody uses HEC-RAS because it's the model to use, right? So if you're going to use dynamic wave, you're going to use HEC-RAS, period. You're not going to sit down to develop a dynamic wave. Why? Because it's too complicated and there's no needed. Besides, who are you going to compete with? You're going to compete with the Army Corps. I submit that you should not compete with the Army Corps because they'll obliterate you. I mean, they are so big that they don't really, pay too much attention to other things that other people do, right? I'm not being negative. I'm just saying that's the truth of the matter. I don't think there's anybody out there trying to compete with the Army Corps of Engineers by developing models that are alternative to the Army Corps. Okay, so that's the end of the story of the fact that Danny Fred did some great work, but his work is no longer used because people have superseded with the Army Corps. Now, the last question I want to say in here is did the Army Corps solve the dynamic wave on the Priceman scheme and so forth? The answer is no, absolutely no. The Army doesn't do that. What the Army did is that they hired a fellow by the name of Bob Barkau. He spelled his name B-A-R-K-A-U, Bob Barkau. In the middle 90s, solved the problem. Doing this, doing that, but he solved the problem. And he had a model that he was running and selling for a while. He was based out of a town in Colorado. And as a matter of fact, I should mention this, that Bob Barkau took a class with me in numerical hydraulics in the year 1979. So he was my student. That 5, 6, 7 years later, Bob developed this method. He got involved into this, and he sold it for a number of years until he finally, at the end of the year 1900, so in other words, 22 years ago, he was basically convinced by, or rather whatever it was, I wasn't there. But basically what happened was that Barkau's model ended up being part of HEC-RAS. And why do I say that? Because HEC-RAS, the manual says it. They said, we use the Barkau model to do this. So his model became part of HEC-RAS. That was the end of his model. Because if Barkau had any desire to sell the model, once he put it into HEC-RAS, he couldn't sell because HEC-RAS is free, right? It's a government model, free. So anyway, I have not been in touch. I used to be in touch with Bob Barkau, but not anymore. I think once or twice in the last 20, 30 years. But that's the end of that part of the issue here. This only to show you that dynamic wave is serious business. Very few people, if any, have actually attempted to do it. Danny Fred had the wherewithal to do it. Bob Barkau did it. Conge did it too. But who else? Professor Chang of San Diego State was doing it, and he did it. He's retired. He's been retired for 15 years. I don't know exactly if he's still using his model. My understanding is that he uses his model in all his consulting. Okay. Your Professor Ponce also had a dynamic wave. But I realized I couldn't do anything with it because I'm going to compete with the big elephants. You can't do that. There's a saying that says that when the elephants dance, the mice get out of the dancing field. It's a very good saying. I didn't invent it. Professor Hobart of geology. No, not geology, biology. I'm not sure. I think he's biology. Professor Hurlbert of biology told me that saying many 25 years ago when we were working on the Salton Sea. Interesting. You never cease to learn. Okay, so that's the story on the dynamic wave. And finally, when to use HEC-RAS. We have 10 minutes, I hope. Okay. When to use HEC-RAS. Let's look at the vector here. HEC-RAS, Hydrologic Engineering Center, River Analysis System. How did that river analysis system be created? Well, first of all, it used to be HEC2, HEC2. From 1968 to 1998, for 30 years, it was the character cell model of the Army Corps for hydraulics. HEC1 was hydrology, HEC2 was hydraulics. In 1998, the Corps created their GUI versions. And so therefore, HEC2 was going to be converted to HEC-RAS and HEC1 and HMS. With the difference that HEC2 only did one part, the steady flow, while RAS does 6 parts, and it's keep adding to the, so RAS is a much fatter model than HEC2 ever was. Can form 5 types of calculations: steady flow, unsteady flow, with the Barkow model. 2-dimensional flow, I honestly don't know where they picked up that model 2-dimensional flow. There was a gentleman that used to do this out of, I believe, Alabama back in the late 90s. And he died young, by the way. He died 50, 55, he died. And I believe after that, I don't know what would have happened to his model. Movable boundary flow, yes, many people have attempted to do movable boundary flow. We have done movable boundary flow too. Temperature and water quality model. And my understanding is that they are working on the 3D model. Hopefully they'll get it out anytime now. The steady flow component uses the standard step method. The unsteady flow component uses a numerical solution of the complete equations of gradually varied unsteady flow, a mouthful, commonly referred to as the dynamic wave. 2-dimensional flow component uses the depth average equations and so on and so forth. Movable boundary model uses the sediment continuity equation, the Exner equation, and one of several sediment transport equations to calculate riverbed degradation or aggradation. Mississippi River near Bemidji, Minnesota. I was in northern Minnesota for a family gathering many years ago, like what was it, 2010, so that was 12 years ago. And I ended up photographing the source of the Mississippi is an outflow of Lake Bemidji in Minnesota, northern Minnesota. So in other words, prior to this photo, the Mississippi is a lake. And then it overflows into this Mississippi. So you can see that's the mighty Mississippi at its headwaters. Or the Channel River, I've shown this picture. When is it necessary to use unsteady flow? This question is of considerable practical interest, since unsteady flow is significantly more complex and requires more data than steady flow and more money. However, the answer is not straightforward, requiring some elaboration. Steady versus unsteady flow. And the steady flow is a simple process. You got a discharge upstream, a stage downstream, and 4 equations on however many equations, 5 reaches, 1 equation per reach, that's right, and you solve a problem. This problem is solved for 100 years, actually 1930, 90 years. The Bresse formulas of the middle 30s, and then all sorts of other formulas, including Professor Ponce's formulas of the 1990s. We have a complete solution of this stuff in our book, in our hydraulics book, okay? Complete solution, why? Because we didn't use the Manning equation. We used the modified chassis, which is my S equal FF square, F root number square. And with that, you can get to the complete answer. With Manning, you cannot. Okay, under unsteady flow, the user specifies a discharge hydrograph at the upstream boundary and a discharge stage rating at the downstream boundary. The model proceeds to calculate discharges and stages throughout the interior points. Under steady flow, the discharge stage ratings are unique. That is, they are the same as in unsteady kinematic flow. However, under unsteady dynamic flow, the model calculates loop discharge stage rating according to the variability of the flow. Therefore, the specification of a unique, that is, kinematic stage discharge rating at the downstream boundary contradicts the solution at that boundary. Simply stated, the wave cannot be kinematic everywhere, but not kinematic, or rather, cannot be kinematic at the downstream boundary and dynamic everywhere else. In other words, you're solving a dynamic equation for all the interior points, but you're stating the downstream point to be kinematic. That, of course, is not natural. That's not the way it should be done, but it is done, by the way. And I'll tell you why later on. So we have a way out of this difficulty, which was discussed by Danny Fred, by way with me. Back in the early 80s, we had a meeting with Danny, and I told him about this. And he said, we solved that problem by extending the channel downstream artificially. I said, oh, really? That's the way we do it too. A way out of this difficulty is to artificially move the downstream boundary further downstream to specify the unique discharge at the new artificial downstream boundary. Like in here, this is where we want it, but we're going to go over here and specify the unique rating. And then when the model comes back, surely it opens up the hysteresis, and then you get your perfect hysteresis and dynamic wave rating in the middle, which is where you want it. This thing works. This thing works completely. And to let the model calculate the loop ratings of all interior points, real and artificial, including the point where the actual physical downstream boundary is located. Well, if this is not complexity, I don't know what it is, but it is done. But let me also tell you, that's a good story. The sad story is that very few people do it. And very few people do it for two reasons. First of all, the unsteadiness is mild. In other words, Leichen and Witter was correct. Most of the waves are kinematic or very mild diffusion. We don't have any real dynamic waves out there to be confronted or to be acknowledged. Therefore, this fancy calculation of the extension may not be necessary. Okay, we're putting it in there because it's theory and it is good theory. It has to be done, but the issue is how important it is. And I believe that in practice, it's not that important because most waves are kinematic diffusing. So the chances of doing this would not be absolutely necessary. And as a matter of fact, I can tell you that for a fact, because I know what I'm talking, that most people in practice don't do it. They do not do the extension that I'm talking about here. So it's a precise, complete extension, but it's not absolutely necessary. And in practice is actually ignored. It is actually ignored. But to ignore means that you know. If you don't know, then you're not ignoring. You're doing something else because you want to do it something else. Okay? Kinematic versus dynamic waves. I'm going to wind this thing up in about 4 or 5 minutes. The decision to use or not to use unsteady flow. Also, here's the question. You have a model that can use steady flow and unsteady flow. So then the answer is, what are you going to do, steady or unsteady? And the answer is, well, it depends. It depends what you want to do. You're selling the model. You're selling the practice to the owner. And who's the owner? The owner is the city of San Diego, the county of San Diego, the county of Riverside, or whatever. But those people, those people that are working for the county are not specialists. That's why they hire you. You're the specialist. You're with a consulting firm. You're in the know. They're not in the know. If they were in the know, they would do it themselves, right? But since they don't know, and besides the practice is to hire it out, they hire you to do it, okay? So you have to tell them, what do you want? Actually, you don't say, what do you want? Because they will back to you and say, what do you recommend that we do? I mean, we hire you to recommend, right? So then you have to recommend, you can recommend the steady or the unsteady. And I'm gonna leave it at that because I don't wanna get into details which are largely political. But the issue is some people actually recommend unsteady. Some people say, hey, don't worry about it. It's steady is fine, which is mostly correct, by the way. So the unsteady is used by some people under unusual circumstances, okay? So it will depend whether the wave being analyzed is kinematic or dynamic. If the wave is kinematic, the discharge will not vary in time. The discharge ratings will be unique. And the downstream boundary condition may be specified as a unique rating because the wave is kinematic, okay? The solutions of steady and unsteady flow are the same. If the wave is dynamic, the discharge will vary in time and space, attenuating as it moves downstream, as accords to a good, well-behaved dynamic wave. The calculated discharge rating will not be unique. For better accuracy, the downstream boundary may be moved artificially downstream, which is what we said, to allow for a loop rating to develop at the actual physical downstream boundary. In this case, the unsteady flow calculation is justified, assuming, of course, that the wave is really dynamic. Okay, now comes the truth of the matter. Use of unsteady flow in channel design. So there's an issue here of design versus what is the other one? Forecasting. Yeah. If you're designing, it's a static situation. In forecasting, it's not static. Forecasting is dynamic, it varies with time and so forth. So the question is, what are you doing here? Are you doing design or forecasting? And I have the answer to that question. You're doing design. You're not doing forecasting, because to do forecasting, you have to be the National Weather Service, work with the National Weather Service, or have been hired by the National Weather Service. And the National Weather Service doesn't hire just about anybody. They hire the big guys, Okay, so if you work in San Diego, excuse me for saying that, it does need to be said. They're not going to hire you. They're going to go out there in San Francisco, Chicago, New York, right? So you're not going to be doing forecasting, not because there is not forecasting being done, but because you as a person will not be hired to do it, but you will be hired to do design, okay? So most of the work will be design, most people, okay? The preceding consideration begged the question of whether a given flood wave can be construed as either being kinematic or dynamic. So is the wave kinematic or dynamic? Or better yet, whether a dynamic wave should be used at all to determine stages in the design of channel improvement, meaning design. On typical projects of limited channel lengths, like this one over here, this is a channel in Florida. I say limited channel length is 4 miles, but 4 miles is not that long. In the great scheme of things, it's not that long. On typical projects of limited channel lengths, a kinematic wave, which keeps its discharge constant, is a more appropriate assumption than a dynamic wave, which attenuates its discharge. In other words, in layman's terms, should you use kinematic wave or dynamic wave for design? And the answer is for design. The answer should be kinematic, because kinematic keeps its stage, and therefore you're going to get the worst situation, the design condition. If you use dynamic, the dynamic is going to lower its stage, and you're not going to know at any one time if the wave is kinematic or dynamic. Therefore, the safe assumption for design purposes is the wave is kinematic. Okay. The kinematic wave assumption assures that the channel is designed to contain all waves, kinematic or dynamic. The stages calculated with the kinematic wave are essentially the same as those calculated using steady, gradually varied flow. Therefore, the use of an unsteady flow feature of HEC-RAS in the calculation of stages in the design of channel improvement projects does not appear to be warranted. I said that for 10 years. And the Army Corps, actually, the Army Corps likes this statement and likes the video, by the way. I'm not going to show the video, we ran out of time. But the Army Corps has not at all argued. In fact, they like this video that we produced. And why do I say that? Because that video gets a lot of traffic. There's more traffic than normal. So it's not Professor Ponce, it's the Corps that is behind that video. And when the Corps puts that video in their website, I get a lot of traffic. That's the way it is. So I'm going to stop in there. And next week, yeah, we go to a different subject. So thank you very much. Thanks for your time. And we're very quickly approaching the end of the class. Thank you very much.